We now come to the final purely measure-theoretic topic for the course, product measure. We've already seen one important example of a product measure, Borel measure, on d-dimensional Euclidean space. We defined Borel measure on Rd to be the sigma field generated by half-open rectangular prisms, that is, by Cartesian products of half-open intervals. And in the usual way, we could replace those with closed intervals or open intervals or half-infinite intervals and so on, piece by piece. Now, this collection certainly includes Cartesian products of one-dimensional Borel sets. And so we can equally conclude that the Borel sigma field over Rd is generated by the Cartesian product of d copies of the Borel sigma field over the reals. That's going to be our definition for product sigma fields in general. Given two measurable spaces, omega-1 with a sigma field f1 and omega-2 with a sigma field f2, the product sigma field, which is denoted this way with a tensor product sign, is defined to be the sigma field generated by f1 times f2. To be more precise, it is the sigma field generated by all sets of the form A1 times A2, where A1 ranges through F1 and A2 ranges through F2. Now, we can do induction on there and use nice natural properties of sigma field generated by to conclude that any finite product, for example, can be written as the sigma field generated by all finite Cartesian products of sets from the sigma fields in the product. We can be more general than that, actually. Like we did up here when we defined the Borel sigma field over Rd, we could restrict not to products of any events from the different sigma fields, but actually only those from subalgebras that we like. They don't even need to be algebras. It's also true that the product sigma field is generated as a sigma field by all Cartesian products of sets A, where those AJs are in some subsets of the sigma fields, provided that those subsets have the property that they contain as an element the whole space, omega j, and they generate the full sigma field in question. And verifying that is part of your homework. In any case, what we've seen from these definitions is that the Borel sigma field over Rd is nothing other than the product sigma field of the Borel sigma field on R d times. Now, another way to verify that, if you don't like working with all of these sets, is to work with random variables instead, and talk about these sigma fields as generated by certain families of measurable functions. And indeed, there is a natural collection that will do the trick. Those are the projection functions. Given any collection, it actually doesn't even need to be finite for any of this to make sense. Any collection of spaces omega j, take their Cartesian product, then we have the natural projections from the product down to the base space, given by picking out the kth coordinate. Of course, to be clear, if we have an arbitrary product here, the existence of these functions is one statement of the axiom of choice. In the finite setting where we're planning to use it, there's no doubt about their existence in anyone's mind. It is then a theorem that the product sigma field that we just defined over here can alternatively be characterized as the smallest sigma field over omega-1 product up to omega d, with respect to which all d of those projections are measurable functions. And that is also on your homework. Now, while we're on the topic of sigma fields generated by measurable maps, let's talk about measurability with respect to the product sigma field in the range. Suppose that I have a collection of measurable spaces and another measurable space, and I have a function from the space upsilon to the Cartesian product that is measurable with respect to this sigma field in the domain and the product sigma field in the range. That map is measurable if and only if the projections of that map into the individual spaces are all individually measurable with respect to these sigma fields. In other words, here I have a vector-valued function. It is measurable if and only if each of its component functions is measurable. We proved that already for Borel measurability. That was really just a special case of this result. So let's prove this. We're going to use the fact stated on the last slide, and that is on your homework, that the product sigma field we're using in the range is the minimal sigma field with respect to which those projections are all measurable. And to save writing, I'm going to give that product sigma field a name. I'm just going to call it F for the rest of this problem. So let's show this if and only if statement. First, we'll show that if F is measurable, then all of the projection compositions with it are measurable. Well, by assumption, F is measurable from B to the product sigma field F, and each projection is, of course, Fk measurable. After all, F is the minimal sigma field with respect to which all of the pi k's are measurable in that way. And so, therefore, the fact that pi k composed with F is Bfk measurable follows by composition of measurable maps being measurable. So that's good. What about the reverse direction? Well, again, the range sigma field F is the product sigma field, which is the same thing as the minimal sigma field with respect to which all of the projections are measurable. So what does that mean? That means it's the sigma field generated by the union of the pullbacks under the projections of the sigma fields Fj. Now, in the usual fashion, it therefore suffices to show that the preimage under F of any set A is in B for all sets A that are in that union. Well, sets A in that union are sets that are in at least one of those pullbacks. In other words, A is equal to the preimage under pi j of some set Ej in the sigma field Fj. So if we have such an A, then the preimage of F under it is the preimage of F on the preimage of Ej. But of course, the way composition works, that is pi j composed with F preimage on Ej. And our assumption for this direction is that pi j composed with F is Bfj measurable, which is exactly to say that this must be in B, which is what we needed to show. So it's easy to handle measurability of functions with a product sigma field in the range. But what about in the domain? That's going to be more relevant for what we do in this and the next lecture. And for that, I want to show you a special collection of functions that do the trick easily. Tensor product functions. Suppose that I have two measurable spaces, omega 1 and omega 2, and two functions, f1 and f2, real valued on each one. Then I can construct a function of two variables, which I'll call f1 tensor f2 on the product space, and it's just defined by f1 tensor f2 at the pair omega 1, omega 2 is equal to the product f1 at omega 1 times f2 at omega 2. We'll use these tensor product functions to great effect in the coming theorem for this lecture. But what I want to point out right now is that all such tensor product functions are measurable with respect to the product sigma field in the domain and the Borel sigma field in the range. And the reason that that is true and easy to see is that we can alternatively write this tensor product as the first function composed with the first projection times the second function composed with the second projection. Here I take a map from omega 1 times omega 2 to omega 1 and compose it with f1. This is the function that takes omega 1 omega 2 to f1 of omega 1. This is the function that takes omega 1 omega 2 to f2 of omega 2. Individually, they are constant in the other variable. Now I take their product, and that's what the tensor product is. But we know from definition that pi1 is appropriately measurable, compositions are measurable, and so this map is f1 tensor f2 Borel measurable, this map is f1 tensor f2 Borel measurable, and products of real-valued measurable maps are measurable, and so this one is indeed appropriately measurable. We're going to use these tensor product functions as a key ingredient in our construction of product measure, which is now where we're heading. Suppose I now have two measure spaces, not just measurable spaces. That is, we have measures on each of the measurable spaces. We would like to construct a product measure on the product sigma field that is nicely related to the two measures. The relation that we want, for better or worse, is this one. If I have a set which is a product, we know that products of this form are among the various sets in this product sigma field. There are many others, but those are some of them, rectangular sets, if you will. Then the product measure on a rectangle should just be the product of the measures of the two sides, if you will. Now, equivalently, we would like our product measure to be defined in such a way that if I integrate one of these tensor product functions against this putative product measure, it should factor as the integral of f1 against d mu1 times the integral of f2 against d mu2. The first statement is a special case of the second if we were to take f1 to be the indicator function of b1 and f2 to be the indicator function of b2. Because as you can readily verify, in that case, the tensor product of f1 and f2 is the indicator function of b1 times b2. It is our desire to construct such a measure, but right now it's not entirely clear how to do that. Let's think back to calculus. If I have a two-dimensional set E, and I'd like to calculate its area, how do I do that? Well, if I go back to the base definition of integrals and areas, and if this is a nice enough set called a pavable set, then I am supposed to break it up as an approximate collection of rectangles and add up the areas of those rectangles, and then take a smaller grid of rectangles and approximate it further. So that's in line with what we were saying on the previous slide, using the definitional area of rectangles to define this. But of course, that's not actually how we would compute the area of this set. The way we would actually compute the area of such a set is as an integral, a double integral. We would take the indicator function of that set and integrate it against dx dy. Of course, what that's going to mean is we'll then evaluate this double integral as an iterated integral, and so we'll say freeze a particular value of x, and then look at the indicator function there, which just tells me when I'm in the set along that vertical line. And then I will integrate the constant function 1 along this vertical line to get the length of that line, and then integrate that function, which represents the lengths of those lines, as x varies. So the way I wrote that, that's the integral of the indicator function of x and y with respect to y, then integrated with respect to x. I could alternatively have decided to freeze a value of y and integrate that way first. So then I would be integrating the indicator of e, x, y, dx, and then integrating that with respect to dy. And of course, I know that I'm supposed to get the same value for each of those iterated integrals. And that's more or less how this double integral is defined in calculus? Well, that's of course relying on an important theorem, that we can evaluate double integrals as iterated integrals for Riemann integration theory. In any case, that's the right way to compute an area like this, and it's going to be the right way to define product measure in general, at least in the sigma finite case where all of this will make sense. So, to really understand product measure, we're going to need to figure out how to do iterated Lebesgue integrals. Well, here's how that works. If I have two measure spaces, for technical reasons they need to be sigma finite for this to work, and actually in the proof we're just going to restrict to the finite case, since the sigma finite extension is not very interesting from there. And suppose that I have a non-negative function, f, which is measurable with respect to the product sigma field and the Borel sigma field in the range. Then the following statements are true. The function is appropriately measurable as a function of each variable with the other held fixed. That is, holding omega 2 fixed, as a function of omega 1, it is f1 Borel measurable. Holding omega 1 fixed, this function of omega 2 is f2 Borel measurable. Since these are measurable non-negative functions, I can integrate them. I might get infinity as an answer, but I will at least be able to give a consistent value for what the integral is. And so we'll do that. So let's take the function of omega 2 with omega 1 held fixed and integrate it with respect to omega 2. That gives us a function of omega 1. That function, which could take infinite values, is f1 Borel measurable. Borel with respect to the extended real line now. And we have the comparable statement for holding the other variable fixed. And then finally, now that I have these two measurable functions that are again non-negative, since they are integrals of non-negative functions, I can integrate them, again, with respect to the other measure that still hasn't been integrated out, and it doesn't matter what order I do that integral. Doing the integral with respect to mu2 and then with respect to mu1 gives the same answer as doing the integral with respect to mu1 and then the integral with respect to mu2. That's our theorem. Iterated integrals make sense in a measure theoretic context, at least for non-negative measurable functions on the product sigma field, when the measures are sigma finite. And as I said, we're going to restrict to the case where these measures are actually finite. This is of course in probability after all, and in fact the extension to sigma finite measures from there is a standard kind of extension and is also pretty boring. So, how are we going to prove this? We're going to prove it in a few steps. The starting point is to prove that it holds true in the special case where the function we're considering is a tensor product function. So that's step one. First, we verify that all three of those properties, the measurability of the half integrals, and the exchangeability of the order of iterated integration, all hold true for tensor product functions. So, suppose f is a tensor product function. That means that f is just f1 of omega 1 times f2 of omega 2. Thinking of that as a function of omega 1, that is just some constant, this constant, times f1. And measurability is certainly preserved under vector space operations, and so this will be a measurable function. No problem. And I'm just going to say that looking at omega 2 going to that function is analogous, just reversing the roles of omega 1 and omega 2. Okay, part 1 done for tensor product functions. Now, what about doing the integral with respect to one of the variables? So let's just compute it in this case. So here we're going to integrate out omega 2 first. So that's f1 of omega 1 times f2 of omega 2, mu2 d omega 2. And again, with respect to this integral, omega 1 here, f1 of omega 1, is just a real valued constant. And we know that the integrals are linear, so we can pull that out. So this becomes that constant times the integral of f2. But now, thinking of this as a function of omega 1, This is just a constant, this constant, times f1, which is, again, measurable as we need it. And this part B, where we look at this as a function of omega 2 and do the integral with respect to mu1, is again analogous. Okay, so now what about the iterated integrals? So in this case, let's do the integral with respect to mu2 on the inside and then mu1 on the outside. This makes sense at least because we've verified that the inside function, the integral with respect to mu2, leaving omega 1 as a free variable, that function is measurable and non-negative, therefore can be integrated. Well, so inside here, this is just as we computed over here, f1 of omega 1 times the integral of f2 d mu2. So we're integrating that. But now this integral is a constant that we can pull out of that integral. And we just get that this amounts to the product of the two integrals, f2 d mu2 times the integral of f1 d mu1. And of course, we can see that there's no preferred order here. This is a symmetric expression. If we exchange mu1 and mu2 and f1 and f2, we get the same answer. And so doing exactly the same calculation, but with the reversed order of integration, I'll get the same answer. And so that concludes the proof here in the special case where the function is a tensor product function. Okay, so now what do? We wanted to verify these hold for any product sigma field Borel measurable function, and these form a very small class of those. So if we were thinking like analysts, what we would try to do now is show directly that any appropriately measurable function can be constructed out of these in an integral-friendly way. For example, we can approximate them by linear combinations of these. And that is true, but we don't need to go back to basic principles to show that. We have a nice tool developed in the last lecture that will allow us to do that extension like magic. And that tool is Dinkins' multiplicative systems theorem. Let's define H to be the set of all functions that are measurable with respect to the product sigma field and the Borel sigma field in the range, and bounded, for which the properties we want to show hold true. We would like to show that actually all of these satisfy these conditions. What we've shown so far is that this subset of them, the set of tensor product functions that happen to be bounded in each variable, do satisfy conditions 1 through 3 of the theorem. Well, we'd like to show that, therefore, this space is big, contains everything that is measurable and bounded. And the way to do that is to show that this is a multiplicative system inside here, and that this is closed under bounded convergence. So let's do that. First, we'll show that M is a multiplicative system, and that's just a bunch of writing. If I take a tensor product function, f1 tensor f2, and multiply it in the range as usual by a tensor product function g1 tensor g2, so that function of the two variables omega 1 and omega 2 is just f1 of omega 1 times f2 of omega 2 times g1 of omega 1 times g2 of omega 2. And all I'm going to do is reshuffle this product and write it as f1 of omega 1 g1 of omega 1 times f2 of omega 2 g2 of omega 2. Because that, by definition, is f1 g1 tensor f2 g2 at omega 1, omega 2. And so we see that that product is again a tensor product function. Also, if I take bounded functions to start, their products are bounded functions. And so we've verified that this set M of tensor product of bounded functions is a multiplicative system. Great. Next, we'd like to show that the sigma field generated by M is the entire product sigma field. But that's almost immediately true because M, the set of bounded tensor product functions, contains the tensor product of any two indicator functions of sets in F1 and F2. And as we already stated, that's the same as the indicator function of the product, B1 times B2, for any B1 in F1 and B2 in F2. So since M contains all of these, it follows that sigma of n contains all of these product sets, and therefore contains the sigma field generated by all those product sets, which is, by definition, this dude here. Great. Now, in order to apply Dinkins' multiplicative systems theorem, we would like to show that H contains M and the constant functions and is closed under bounded convergence. Okay, so M is contained in H. We already noted that. That was what step 1 was showing, that if I have any tensor product function, conditions 1 through 3 hold, and adding this new boundedness constraint is fine in this context. Constant functions are tensor product functions. 1 is constant 1, tensor constant 1. And so M union 1 is just M. Okay, so by step 1, we've already verified this. So now what we need to do is verify that this space, the space of bounded functions for which 1 through 3 hold, is closed under bounded convergence. Well, let's go back and stare at those conditions. If I have a sequence of bounded functions f for which these conditions hold, and those functions converge, the boundedness doesn't matter here. By the robustness of measurability, I get that the limit function also satisfies the measurability criteria. So that one doesn't even require bounded convergence. Condition 1 holds under convergence. But condition 2 involves integration. So now what I have is a sequence Fn that converges to some f in a bounded manner. And I want to verify, given that each Fn satisfies this condition, that the limit function does. Well, that's just a statement of transferring a limit pointwise to a limit of integrals. And we have a tool for doing that, the bounded convergence theorem. In general, we have the dominated convergence theorem, but the best we're going to be able to use as a uniform dominating function here is a constant function. And that's going to work fine under our assumption of bounded convergence. But here we see why we need to make the assumption that these are finite measures, because constant functions are only L1 dominating functions if the measure involved is finite. But that's okay. Dinkins' theorem is usually a tool that applies in probability settings for this very reason, and we are in a probability course. So, by using the dominated convergence theorem with a constant bound as the uniform dominating function, we verify that condition 2 holds under bounded convergence. And similarly, by a double application of the dominated convergence theorem with the uniform constant bounds, we'll get that condition 3 holds under bounded convergence. And so just by staring at these hard enough, we see that, indeed, H is closed under bounded convergence. Thus, by Dinkins' multiplicative systems theorem, in this finite measure context, we conclude that H contains the space of all bounded functions on the product that are measurable with respect to sigma of m, but we verified a moment ago that sigma of m is equal to the full product sigma field. And so we have now, in one fell swoop, verified that all bounded measurable functions, measurable with respect to the product sigma field, satisfy these iterated integral conditions that we're trying to prove hold. And that's almost the full statement of the theorem that we want. We wanted to show that it's true for all non-negative functions, and what we've done is to show that it's true for all bounded functions. So now we need to do one further step of approximation, and take a non-negative measurable function and approximate it by bounded functions. So here's how we do that approximation. Take any non-negative product sigma field Borel measurable function, and take any cutoff, I'm going to use integer cutoffs, and define fn to be the cutoff of f by n. That is, fn is equal to f unless f is bigger than n, in which case it's just n. So this is a bounded function, and of course it is measurable on the same sigma fields that the original function is measurable, because as we showed, a minimum of two measurable functions is measurable, and constants are always measurable. Now notice that this sequence fn is pointwise increasing, because by taking the cutoff at height n plus 1 instead of n, all I'm doing is modifying the earlier cutoff by allowing the function to take the place of n on places where it was already bigger than n. So I'm modifying the function to be something bigger than n on the set where the function was between heights n and n plus 1. So I can only increase the function by doing so. And moreover, it increases to the original function f, because f is real valued. Which means that for any omega, there is some n, so that f at omega is less than or equal to n. As I remove those n cutoffs, I will eventually recover the function everywhere. Okay, well, by step 2, we showed that fn being in here satisfies conditions 1 through 3. It satisfies the iterated integral conditions. And fn increases to f, so now if we go back and stare at those conditions one more time, we see that if I have a sequence of increasing non-negative functions converging to a non-negative function, that each of these conditions must transfer from the sequence to the limit. Here again, just by the robustness of measurability under limits, and in these cases where we have to exchange a limit and an integral, this time that will be justified by the monotone convergence theorem, again twice in the iterated integrals down here. If you want to write out all those details, be my guest, but I'm going to call this theorem proved. Great, so now what? We know that all functions that are non-negative and measurable with respect to the product sigma field can be integrated in this iterated fashion. Well, that's what we wanted to do. We wanted to develop an iterated integral and show that the order of integration doesn't matter in order to define product measure. And so that's where we are now. The theorem, which is a simple corollary to what we just proved, is there exists a unique measure called mu1 tensor mu2, where again, in the case here where mu1 and mu2 are assumed to be sigma finite, for all of this to work, this so-called product measure is a measure on the product sigma field, and it satisfies the rectangle condition that the product measure of a product set is the product of the measures of those two sets. Moreover, this condition uniquely specifies one measure. There's only one measure that does this. And what is that measure? It's defined as an iterated integral. The product measure of a set E you calculate by doing an iterated integral of the indicator function of E against the two measures in either order, because the order you do them in does not matter. And a consequence of this, as you can readily see also, is that the product measure in this case is sigma finite. So how does this work? Well, all we need to do is verify that this, which is equal to this by the theorem, defines a measure. Well, let's check finite additivity. So mu1 tensor mu2 is finitely additive. And that follows from properties of integrals that we've developed simply because the indicator function of a disjoint union of two sets is the sum of their two indicator functions. And integrals are linear. So if we just plug this in over here, then this inside integral will become a sum of integrals, and the outside integral will then become a sum of iterated integrals by linearity. So that shows that the measure mu1, mu2 defined like this is at least a finitely additive measure. Now, in order to show that it's a genuine measure, to show that it's countably additive, it suffices to check that it's continuous in the sense that if I have a sequence En of measurable sets in the product sigma field that increases to a set E, then the measure, the product measure of En, should increase to the product measure of E. Well, this implies that the indicator function of En increases pointwise to the indicator function of E. These are non-negative measurable functions, and so the inside integrals will have the same property, that the integral with respect to one variable of this increases to the integral of this by the monotone convergence theorem. And then we'll get the same increasing property for these as functions of the other variable, and apply the monotone convergence theorem again to the double integral. And so we will therefore get that the product measure of En increases to the product measure of E by the monotone convergence theorem. Okay, so this thing defines a measure. Is it a measure that satisfies this rectangle property? Yes, because the product measure of a product set is the iterated integral of the indicator of that product set. But the indicator of a product set, as we've verified already twice, is the tensor product of the indicators of the two. And as we verified early on in this lecture, an iterated integral of a tensor product function just gets computed as the product of the integrals of those two functions, which is mu of E1 times mu of E2. So this does define a measure, and it satisfies the rectangle area condition. So we just need to check that it's the unique one that does that. But that follows easily from the fact that the product sigma field is generated by all product sets like this. And so once we know the measure on a generating family, we know it everywhere. And so that concludes the proof. So now we have product measure. What we've left to do is figure out how to integrate functions against it. Well, hint, we already saw how to integrate positive functions against it on the last slide. They're iterated integrals. But we're also going to need to integrate L1 functions against it and understand what those L1 functions look like. So that's what we'll do in the next lecture.